Let us now learn about the concept of electric current. This battery is making this bulb glow by putting in a potential here which is 10 volts at A and a potential at B which is 4 volts. So there is a potential drop from A to B. This battery sends a charge, let us say 2 coulomb charge to A. When this charge is at A, it has a potential energy of 2 into 10, 20 joules. Now remember this 20 joules, though we have written it as PE at A, it is not the potential energy of the point A. It is the potential energy of the charge when it is at point A. It is the potential energy of the charge. Okay, so when the charge moves from here into the battery and goes to the other side, it only has a potential energy of 8 joules. So that means the charge has lost 20 minus 8, 12 joules. So that 12 joules is what makes this bulb glow, right? So, but if this happens only once, that is, this charge travels from the battery and it's not going to stop there, it's going to go back, right? We are not losing the charge. The charge that came from the battery is going back into the battery. So only the energy of the charge is transferred to the bulb. But if it happens only once, that means this bulb will glow for a fraction of a second. That's not what we want. We want the bulb to keep glowing. So that means we must have continuous flow of charge. So charge Q is going through, notice it's going through the bulb, transferring energy, going back into the battery, getting some energy from the battery, again going through the bulb. So this is a continuous process. So when charges move like this continuously, then we say that we have an electric current. So what is electric current? Continuous flow of charges, right? Okay, now if you think a little bit about this, the energy received by the bulb is actually every second it is receiving because there are charges flowing through the bulb every second. Because every second the energy lost by the charge is the energy gained by the bulb. So that means each second how much charge passes through the bulb, that matters, because that is what is going to transfer energy to the bulb. So that gives us a very nice way to measure electric current. So electric current is measured by the amount of charge that flows through the bulb or through any circuit every second. So the amount of charge that flows every second tells us how to measure the electric current. Let us now look at the direction of electric current. Here I have some charges, positive charges, that are flowing in this direction. The direction of flow of positive charges is defined as the direction of the electric current. How did that come about? Actually, in 1750s, Benjamin Franklin did a lot of research on electricity. He found out that there are two kinds of charges. He wanted to call them positive and negative. Of course, he had no way of knowing which was the charge that was moving. So he assumed that one of the charges was moving like that, and he decided to call that the positive charge, and he thought the other one which was not moving is the negative charge. But unfortunately, he had made a mistake. 150 years later, J.J. Thomson found out that the actual charges that are moving was the negative charge. But it doesn't matter because the negative charges are moving like this, and if the negative charge is moving like this, it turns out that the current is still in the same direction. So Benjamin Franklin's definition of the current direction still stands. So still we use the idea that positive charge movement direction is the current direction, though we now know that in most wires, in most cases, it is the negative charges that are moving, but they are moving in the opposite direction. So the flow is the flow of negative charges, and the current direction is that way, which is opposite to the flow of negative charges. We will still use the definition that the flow of positive charges, the direction of flow of positive charges is the current direction. Is that understood? Let us now look at the proper definition of current. I have here positive charges flowing that way. Now if I ask you how much is the current, we can ask current through this wire. There is a charge here, there's a charge there, there's a charge there. Should we count all of that? No, you have to be very careful because actually current is defined for a cross section area. So you make a cross section of the wire, look at that area through which all these charges are going in, right? So how much charge goes through that area every second? So the definition of current is the net charge that crosses this area divided by the time. Charge is measured in units of coulomb, time is in seconds. So the unit of electric current is coulombs per second. We also call this ampere. So 1 coulomb per second is 1 ampere. So ampere is the SI unit of current. Let us now look at this question. In a time interval of 20 seconds, it is observed that 5 coulombs of charge passes through a cross section of the wire. Find the current in the wire. So now I have a lot of these charges flowing. Through this cross section, there is 5 coulombs that is passing through in 20 seconds. What is the definition of current? Net charge crossing the area divided by time. Here, of course, we are assuming that the charges are flowing at a constant rate. Only then you can talk about the current. The symbol for current is I. So we usually use I to talk about current. How much charge flows through? 5 coulombs. In how much time? In 20 seconds. And so 5 by 20 is 1 by 4 coulombs per second, which is amperes, or 0.25 amperes. So the current flowing through the cross section is 0.25 amperes. But throughout the wire, it is the same. You could have picked that cross section, you could have picked this cross section. Whichever cross section you pick, same amount of current will be flowing. So the current in the wire or flowing through the wire is 0.25 amperes. You can say current flowing through the cross section of the wire or current flowing in the wire is 0.25 amperes. Let us now learn about a very important sign convention. When you have a wire with nothing marked on it, then if there is charge flow in this direction, we can say there is a current of 3 amperes flowing in this direction, right? But if there is a charge flow in the opposite direction, we would still say there is a current of 3 amperes, but it is flowing in this direction. So either way, we will say the current in the wire is 3 amperes. Usually we just talk about the magnitude of the current. So when somebody asks you what is the current in the wire, but no direction is mentioned, give the positive value of the current. But sometimes an arrow is marked on the wire. So now this means that current in this direction is considered positive. So if somebody asks you what is the current I, if there is 3 coulombs per second flowing this way, that means the current in the wire is plus 3 amperes. You can just say 3 amperes. 3 amperes or plus 3 amperes means it is in this direction that is marked. On the other hand, if I had 3 coulombs per second traveling that way, the current is actually flowing this way, right? It's going opposite to I. So what is I equal to? We will write minus 3 amperes. But there we wrote 3 amperes, but that is because there was no sign marked, no positive direction marked. So positive direction could have been like that or like this, it doesn't matter. But here the positive direction has been clearly marked. So current I is minus 3 if the charge is flowing this way. That is, if the current is actually flowing like this, the current I will be minus 3. But if the current is flowing in the direction that is marked, it will be considered as plus 3 or just 3. You don't have to say plus, you can just say 3 amperes. Now remember that electric current has a plus minus sign, but that does not mean it is a vector. For example, the current can flow like this, it can flow like that. It is all considered the same direction. So here, suppose I draw a wire like this and I mark this as the positive direction. Here when the current is flowing like this, it will be considered plus 3 amperes. When the current is flowing like this in this direction, also it is plus 3 amperes. When it is flowing like this, now this direction and this direction are opposite directions if you think in vector terms. But as far as current is concerned, this is still plus 3 amperes. Will you consider this direction and this direction as the same? No. As vectors, these are opposite directions. But in current, current is not a vector. In current, all we care about is that it is flowing along the wire like this, or is it flowing like that? If it is flowing like this, it is all considered positive. If it is flowing in the opposite direction, it is considered negative. I hope you have understood that current is not a vector, but it has a sign. It could be +3, it could be -3. In this question, we have been given a wire AB with the current direction marked. So that means this direction is considered the positive direction. Okay. So we have the first part of the question says 5 coulombs passes from A to B. So from A to B in that direction, how much? 5 coulombs passes in 4 seconds. So the current should be charge divided by the time. 5 coulombs by 4 seconds is 1.25 amperes in that direction. But what is the positive direction? This is the positive direction. So I must be minus 1.25 amperes. 1.25 amperes like that is equal to minus 1.25 amperes along the direction given. Let us now look at the second part. So in the second part, we have 2 coulombs passing from B to A. So 2 coulombs goes from B to A in 5 seconds. So the current should be 2 coulombs by 5 seconds, which is 0.4 amperes. 0.4 amperes in this direction, that is the direction given. So I is plus 0.4 amperes or just simply 0.4 amperes. You don't have to write the plus. Now let us look at the third part of the question. Minus 7 coulombs passes from A to B in 2 seconds. So I have a negative charge going from A to B. I have minus 7 coulombs going this way. Okay, so I can calculate the current by saying minus 7 coulombs by 2 seconds minus 3.5 amperes. But minus 3.5 that way is the same as plus 3.5 this way, and 3.5 this way is the direction we want. So I is plus 3.5 amperes. You can also understand this by saying that if negative charges move from A to B, it is the same as positive charges moving from B to A. So instead of saying minus 7 coulombs goes this way, we could have said 7 coulombs goes from B to A, which will mean 7 by 2, 3.5 amperes from B to A. That is the direction of I marked. So therefore I is 3.5 amperes.